Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Alright, for this one, let's start by drawing a little diagram of the situation that we have. So we're told we have two wires. I'm going to number the wires just to keep them separate. We have wire 1 and wire 2. Now, we're told that they both have currents, but they're in opposite directions. So now this is arbitrary. I'm just going to pick up for 1 and down for 2, just to show that they are in opposite directions. We are also told that they are in a magnetic field that is 65 degrees to the wires. And this magnetic field is present everywhere around the wire. So if we were to draw a orthogonal line to the wires, this angle here would be 65. And this field is everywhere present along the wires at the same angle. Okay, all the things that we are given, we're given the length of both wires. They are equal. So we don't need to worry about two different lengths. We are given the current for the first one, wire 1, which I will call I1 for current 1. Current 1. We are given the magnetic field, the magnitude of the magnetic field, and the direction, which we have is our angle. We're given B. And we are given the net force. And we'll get into exactly what that means in a little bit here. We're going to call it F sub net. Okay, so we have all of these variables here. It's very likely that the equation that we're going to use that involves all of these is the equation for the force, which says that the force is equal to the current times the length through which the current is traveling, the current I times L times the magnetic field B, sine of the angle between them, or sine of theta. So this is the equation that we're going to want to use here. So now how do we incorporate this net force? So that means that's the force over the entire system. That's the force both of these two wires together experience. So now we have one wire that has a current flowing up and one wire that has a current flowing down. This means that the net force is going to be the sum of these two, but the force is going to be in opposite directions. So what that means is our net force in this case is equal to the sum of these two, but because they're in opposite directions, we're going to have a minus sign. So now, because this is physics, we get to decide what directions we want to be positive and what to be negative. And it doesn't matter what we choose, we just have to keep it consistent. We could say up is negative and down is positive. But it's just kind of a general idea to have down as negative. That's how a lot of things have it. If you want to keep it similar to a lot of things you've seen before, we can have down as negative. And what that means is, so F1 is for the first wire. What that would mean to have down negative is that F1, or the F net, is equal to F1 minus F2. The total force from the entire system is equal to the force from the first wire minus the force from the second wire. Okay, So now we have an equation that relates our net force here to our individual forces. That also means that we're going to have to use two different equations to get what we're looking for. So what we want in this case is the current in the second wire. So we want I2. That's what we're trying to find. And now we have to use everything that we're given to do that. So the first step here, we have everything that we need to find F1. We have the length of the first wire, we have the current of the first wire, we have the magnetic field. And that's everything we need, and we have this angle. So all you have to do is plug those in, write an equation out for F1. So really the only thing that's going to be different is the current here, because they both have the same length and they are both in the same magnetic field at the same angle. So you simply have to plug in those values to this equation using 65 as your angle, sine of 65. And then you'll have your F1. Okay, so now for the second equation though, for F2, we're missing a couple things here. We can't just straight up plug it in. We're missing I2, and we don't have a force for the second force here. We don't have F2. But we can do a little bit of math here and get an equation for it. And this is also going to be the same angle. Okay, so now how do we get an equation here? We have two variables in this equation, so we can't currently solve it. F1 is unknown and F2 is unknown and I2 is unknown. But we found F1 and we know what F net is, so we can rearrange this equation to solve for F2. We can say, I'll do it in two steps here. So if we were to subtract F1 from both sides, we get F2 is equal to F net minus F. I'm just going to call it Fn for brevity. F net minus F1. And then we can multiply both sides of this equation by -1, just so we have a positive value for what we're looking for. F2 is equal to F1 minus F net. And we know what both of these things are. We just solved for F1 and we were given F net. So now we can plug in this value into this F2. So now all we need to do is rearrange this equation to solve for I2. Which is just some algebra here. So we want I2, that means we have to divide by all of this stuff. So we have F2, which we have solved for here, is simply F1 minus F net. I'm just going to keep it as F2 for now. Divided by all of that. L B sine of 65. And this will give you what the current is on the wire number 2. This will be your final answer. And there you go.